Okay. Hello, everyone. I'm Fang Li. First, many thanks for inviting me to give this talk. Today, my presentation is about global fire simulations in CMIP Earth system models. This work is a team effort, and I'd like to thank my co-authors for their contributions. If you are interested in more details, you can find them in the paper I've listed here. Next. Hi, Paul. Next. Okay. Let's start with some background. Fire is the primary disturbance in terrestrial ecosystems globally. Each year, it burns over 400 million hectares of global vegetated land. Fire is also an important Earth system process. It is regulated by climate, ecosystems, and human activities, and feeds back to them in multiple ways, both locally and remotely, across various temporal and spatial scales, resulting in intricate feedback loops. For example, fire can affect climate not only by changing the terrestrial ecosystems, but also by emitting aerosols and trace gases. Next. Although the global burn area has declined over the past 2 decades, mainly due to human suppression, the frequency and the intensity of extreme fires and the forest fire emissions have increased. Next. Importantly, in the future, burned area is projected to rise across most biomes of the world, especially under weak climate mitigation scenarios. Next. Next. Due to the critical role of fire in the Earth system, currently most Earth system models incorporate fire modeling. In CMIP upward, the last one, go back. Paul, go back. Oh, okay, here. Okay. In CMIP 6, 19 models submitted fire simulations compared to only 9 for CMIP 5. In CMIP 6, 9 models provided burned area simulations, and 18 models provided fire carbon emissions, which are the two most important fire-related variables. CMIP 6 models used 3 fire schemes: global firm, which were so the fire scheme most used in CMIP 5, Spitfire, and my fire scheme, which is the most used in CMIP models. The present will answer how well do these models simulate fires. Next. Next, we introduce the data. We used CMIP 6 and CMIP 5 historical fire simulations. All fire models used in CMIP 6 are process-based, simulating the fire occurrence and the fire spread process. Among them, global firm and Li are intermediate complexity, and Spitfire is complex. To account for the uncertainty in observations, we used multiple benchmarks for both burn area and fire carbon emissions. Next. Next, let's look at the evaluation results, starting with the global burn area. In this figure, the dashed line is the average of observations, and the shaded area is their range. The bars are model simulations. The last two are the CMIP 6 and CMIP 5 ensemble means, with area bars indicating their multimodal ranges, representing simulation uncertainty. As we can see, 6 out of 9 CMIP-6 models simulate present-day global burn area within the observational range. One critical issue in CMIP-5 was the severe underestimation of the global burn area, with values less than half of the observations. CMIP-6 has addressed this issue. However, CMIP-6 shows larger uncertainty, primarily due to the 3 models using global firm. Next. For global fire copy missions, most CMIP-6 and CMIP-5 models are close to the benchmarks. CMIP-5 models produced reasonable emissions despite very low burn area by assuming unrealistically high combustion completeness for woody tissues. Next. Now let's move on to the spatial pattern. For burn area fraction, CMIP-6 models successfully capture the high values in Africa, whereas CMIP-5 models fail to do so. The spatial correlation with observations is significant for CMIP-6 and double the scale of CMIP-5. For fire copy missions, CMIP-6 also performs better than CMIP-5. Next. For seasonal variability, CMIP-6 models capture the main features of the seasonal phase, that peak months vary from the dry season in the tropics to the on season in the extratropics. They also address one critical CMIP-5 issue, the severely underestimated magnitude. You can see the blue lines in the figures are very flat. Both CMIP-6 and CMIP-5 models fail to capture the spring peak in the northern middle latitudes, mainly due to underestimated crop fires, because assuming no fire over croplands or calibrating parameters based on GFID 3. Next. Let's look at the trend. Since 1850, CMIP-6 simulations generally align well with charcoal reconstruction. However, after 1990, discrepancies emerged in temperate North America and Europe, where models show an increase while charcoal data indicate a decrease. Next. For recent decades, in observations, fire have significantly declined. CMIP-6 models fail to capture the decline, mainly due to underestimating the human separation. For example, models do not consider the influence of landscape fragmentation on fuel continuity. Next. In addition, we assess the relationship between fire and important drivers. In observations, burn area fraction increases fire with population density due to increased human ignitions, then fails due to increased fire suppression. Where CMIP-6 models can capture the relationship except EC models with global firm, which does not consider human ignitions and separations. Next. For the relationship between tropical burn area fraction and precipitation, observations show a clear unimodal pattern. Most CMIP-6 models can capture the relationship except for models using global firm. But war models underestimate fire sensitivity to wet dry variability. In the figure, the vertical axis for the simulations are much smaller than that of observations. Next. In addition, coupled CMIP models are free running and driven by anthropogenic forcing, so they don't aim to align with specific years. Therefore, instead of evaluate the fire interannual variability, we assess how well models capture the fire responses to ENSO, dominant climate oscillation on the interannual timescales. In the figure, the first bars with star represent observations, while the other bars are simulations. As shown, CMIP models generally capture the relationship between fire, interannual variability, and ENSO. Models using Li and global firm perform better than those using Spitfire, labeled as S. Next. To summarize, CMIP models perform well overall. It resolved CMIP 5's three key issues, including low global burn day totals, poor spatial patterns, and low seasonality. Next. Why CMIP 6 performs much better than CMIP 5? It's mainly due to the development of fire skins. The most used fire skin has evolved from the global firm in CMIP 5 to the Li skin in CMIP 6. The Li skin has a better burn area core equation, and its parameters can be calibrated. In contrast, global firm estimates the annual burn area fraction as a nonlinear function of fire occurrence probability. Because the probability can't exceed 1, it underestimates burn area in great cells with multiple fires in a time step. Additionally, fire occurrence probability lacks observations, preventing parameter calibration. Attempts to annihilate to model fire seasonality using a running mean method still resulted in very low seasonal variation, as shown earlier. Next. In addition, challenges remain. CMIP 6 models still fail to reproduce the recent decline and the northern middle latitude screen peak, and underestimate the sensitivity of fire to wet dry variability. Recent advances in fire modeling aim to resolve these issues. Next. Let me briefly introduce the targets and protocol of FireMIP in CMIP 7. Unlike earlier FireMIP efforts, which relied on offline and online simulations, FireMIP in CMIP 7 will focus on the coupled model simulations. FireMIP in CMIP 7 has three targets. First, fire simulation evaluation to understand bias and guide model development. For this target, we will use historical simulations in DEC and land-based simulations in fast track. We want to assess fire changes and drivers in the past, present, and future, including uncertainties. Besides the historical simulations, we will use the scenario MIP experiments to analyze the future fire changes under different scenarios, and dynamics experiments to assess the anthropogenic influence and the influence of anthropogenic aerosols, greenhouse gases, and land use change. Next. We also want to quantify the cross-sphere impacts of fires and fire changes and understand the underlying mechanisms. This is optional, and model groups can choose 1 to 4 experiments based on their scientific interests. Impacts of fires, fire aerosols, fire changes, and fire aerosol changes. Next. Unlike earlier studies based on offline and online simulations, which only allow us to analyze fire impacts on land process and land carbon budget, were those using fixed or prescribed sea surface temperature that lack many important climate feedbacks. For example, aerosol's hydrologic snow response. Carbon model simulations now allows for the first time to quantify the influence of fire and fire change on the land, ocean, atmosphere, whole carbon cycle, and the fire emission impacts on both local and remote climates. Additionally, the use of multi-model and multi-initial condition ensemble simulations helps quantify uncertainties and enhances the reliability of our conclusions. Next. Okay, I'll stop my presentation here. If you are interested in discussing the protocol or analyzing CMIP 6 FireMIP simulations on a specific topic, please feel free to reach out. We'd love to collaborate with you. Thank you for your attention, and I'm happy to take any questions.